For example, let's say you have a transmission line with the input impedance Z in, and the transmission line length is lambda over 4, and it has a characteristics impedance Z naught. If I short this line at the end, so quarter wavelength transmission line with the end shorted, it can be realized using a lumped LC equivalent circuit. The quarter wavelength transmission line with the end shorted, shorted, short circuit can be realized with a parallel resonant circuit. This kind of applications have some practical use in RF microwave circuit. We will look at that later. So for example, in this case, your inductance can be found by using this formula, 1 over omegas naught squared C. That will give you the impedance, the value of the inductance. The capacitance value, once you find the inductance, the capacitance, or maybe you'll find the capacitance first using the formula, 1 over 8 F naught Z naught. F naught is the frequency of operation. Z naught is the characteristics impedance. In this formula, the inductance, you'll find the capacitance first. 1 over 8 F naught. These formulas all can be derived, but we are not showing here because this is outside the scope of this course. So capacitance is 1 over 8, the frequency of operation multiplied by the characteristics impedance. Once you find the capacitance, you take it and put it inside here, and then you'll find the inductance. The inductance will be 1 over omega naught squared C. Omega naught here is in radian second, F naught here is in hertz. And you know they are related by omega naught is 2 pi F naught. Similarly, a shorter half a wavelength transmission line. So now we have a transmission line with the end, the length is half wavelength. The characteristics impedance Z naught. If you short this transmission line can be realized with a parallel series resonant circuit. With the inductance value given by this formula, the capacitance value given by this formula. Okay. So these are some of the things the RF engineer must know, because when you go and look at a microstrip circuit, So what they're doing actually a half wavelength microstrip line, if it's shorted like this, then actually they are in. These are the few things I'm showing you just to make you aware. Similarly, you also can implement similar resonance circuits with open circuited quarter wavelength transmission line. Open circuited. So open circuited with the length, quarter wavelength resonance circuit. We already discussed what are those resonant and parallel circuits earlier, remember? I hope you guys still remember. Resonance circuit, a series resonance circuit will short circuit at the resonant frequency or operating frequency. Later on, we will look at an example. And also another case, earlier on we talked about only short circuited half wavelength and quarter wavelength. Now we're talking about open circuit, half wavelength and quarter wavelength. Now we have 1/2 wavelength open circuited transmission line. This is equivalent to a parallel lumped element LC circuit. Okay, you are not required to memorize these things, but just make you aware. But maybe some things you have to, because these are the things that as an engineer, you're not going to be memorizing this by heart unless you are working in that field for a very long time. By second nature, you will know what they are. But if you're a new engineer who are not used to this, you always have reference books, cookbooks that we can refer these things to. So here's an example to reinforce this concept. So far, any question?
No, sir.
Okay. you have a quarter wavelength transmission line. I showed it at the end. With the characteristics impedance Z0 is 50 ohms. Now I'm asking you to find the lumped element LC equivalent circuit. At the operating frequency or standard frequency, F0 is 1 gigahertz. Okay, go ahead and
4, sir.
Yes, sir.
number four is half wavelength.
The first, sir, first.
First one, okay. First one, quarter wavelength and shorted. So this is this is the model that we need. So now you go ahead and calculate your L's and C. Calculate L and C. So of course, you know, you want to calculate C first because L is dependent on C. L is dependent on C. So you're going to calculate C first. C is 1/8 F0 Z0. Is 1/8 times the frequency was 1 gigahertz. So 1 times 10 to the power of 9 times 50. So that's going to give, if you punch it in, it will give you around 2.5 picofarad. If I'm not mistaken. So once you have your power of minus 12, so go ahead and, so for example, if you want to simulate a transmission line, you can use a voltage source or current source or current source. You know what to do. You just want to look at the input impedance. You just want to make sure the input impedance for both the case are the same. Let's say if I'm using a current source, then the transmission line, your grounded transmission line, then with the proper impedance Z0 is 50 ohms. And then since it's the quarter wavelength, for quarter wavelength, how much is that in degrees? Quarter wavelength convert to degree is how
90.
much? 90 degrees. So 90 degrees. So therefore, you go and choose your E to be 90. So if you want to operate at 2 gigahertz, then you choose 2 gigahertz. You define all these things. That's simple. How long does it take to simulate the circuit? At most 15 minutes, you'll be done with this. Okay, then you compare that with the schematic. Let's say if you're using current source, of course, you know, here you have to define something. Make sure I don't know how you're going to define. You're going to have a polar. There's many ways to define. You just apply a voltage here. LAC, something like this. But you can do your own way. ampere. And then on this, and then you use the same current source for the then for your C and L that you calculated values. Compare FC, same 2 gigahertz, Z naught equals to 50, omega C. So you compare these two. This is your next lab. Your lab must be neat. So you compare these two things. I already told you earlier what to compare. So like for today's lab, it's the lab number 1 is due today. So all of you are going to get 0. I haven't received anything yet. By 12 midnight, you must submit. Otherwise, it's 0. I've given you 3 weeks. Hello? Are you all willing to receive 0 or you want an extension?
Extension, sir.
Whose voice is that?
Is mine.
Huh?
Prithviraj, sir.
Huh?
Sir, Prithviraj.
How about the other guys? Do an extension.
Yes, sir. Extension.
Okay, I give you until Friday, you know. Friday almost ending. Friday, that's
Okay,
it.
sir.
After that, I will be 0. You don't have anything, you don't end in something. If you end in something totally irrelevant, that will be 0 also. Okay, let's continue with this. So the application. So this is for the lab part. So now we're going to use, look at the application of this concept here. RF circuit. RF circuit with a transmission line. And then this transmission line is connected with a capacitor like this, a C. And then it has a characteristics impedance and its quarter wave length. Frequency, center frequency. If this capacitor at F naught, if C is large enough, the output can short. A short or bypass, you know, it's just like short circuiting this line. So then what will the RF circuit see? RF circuit will see a parallel resonant circuit, Z in and FC. The RF circuit will see an open circuit at the frequency of operation. Because if you go back here for quarter wave length, okay, we already went through this the last time. Parallel resonant circuit at the frequency of operation will be open circuit. If you want the RF circuit to see an open circuit at the frequency of operation, and then you can implement that with a transmission line that is a quarter wavelength and terminated with a capacitor large enough so that at particular frequency it will present a small impedance. It will behave like a short. It will be a short circuit. Short circuit means, what I mean by short circuit, the capacitor is large enough so Z in, not Z in, ZC in this case. ZC is 1 over j omega C. Z is 1 over j omega C. It will be like almost zero short circuit. But what the RF circuit will see, the Z in, what you see from here is open circuit at a quarter wavelength away from the load. Any question?
No, sir.
No, sir.
So this is called a, so this will be like open circuit, and this is called RFC. But do you know what RFC stands for? RF choke. Choke. RF choke will block the RF. It is for blocking RF. It is for blocking RF signal. So we are not doing anything complicated here. All I was trying to say was that this transmission line, all this transmission line with a different wavelength, quarter wavelength and 1/2 wavelength with either open or short circuit at the end, can be represented by a lumped LC circuit. Then the lab is quite easy. If anybody is having any problems with the simulation, then you should contact me. You don't contact me on the day when it's due. Okay, next example. Okay, you have a circuit diagram here with the transmission line. The circuit has an input voltage AC with the amplitude V naught cosine, frequency omega naught. And then you have the source impedance Z naught and the input voltage. Looking at the beginning of the transmission line is V1T. The length of the transmission line is quarter wavelength. And the characteristics impedance here, let's say you call this a ZB or something. You don't know what it is. The voltage across. This is the load with impedance 2 Z0, and the voltage here is. Okay, now the question is find V2, the voltage at the load. How do we find that? If this was a regular AC circuit And then you would say, okay, this is Z naught. Okay, this is 2 Z naught. 2 Z naught, and then this is the voltage V naught something. This is a low frequency circuit, then say no problem. V2 is 2 Z naught over Z naught plus 2 Z naught multiplied by V naught. That's quite easy, isn't it? It's a low frequency circuit, but at high frequency circuit, we have to consider the existence of the transmission line. That's going to complicate things. So how do you proceed doing this? First thing you want to do is you want to find the input impedance. Input impedance, looking inside here. Input impedance. Okay, guys, remember what is the formula for the input impedance? With a transmission line. Who can remember? Okay, this is the input impedance. That is including the transmission line. So when the length is, so right now, what is our length here? What is the length of the transmission line?
Lambda over 4, sir.
Okay, depending on the length of the transmission line, the Z in can be different. When the length is lambda over 4, quarter wave length, the Z in will be purely real. When the length is lambda over 2, at certain wavelength, it can be a short circuit, open circuit, or it can be a complex impedance. So in this case, you know, last time we did Z in is going to be just Z in, ZL. I'm doing this again to show you. Although this is electromagnetic, but I'm spending some time here. Beta is 2 pi over lambda. L is lambda over 4. So these are all electromagnetic stuff. Because you guys were not paying attention, I have to do this again. JZL tangent 2 pi over lambda. If I'm going to go through backup and review stuff again and again, that's going to slow us down. So can you guys please help me to solve this? Okay, just tell me what this is. Tangent 2 pi over lambda multiplied by lambda over 4. What is that equals to?
So it's tangent 1 over 2 pi, sir.
Tangent
1 over 2 pi.
Tangent 1 lambda, how can be 1 over 2 pi? Pi over 2, you said. You're trying to say pi over 2, right?
Ah, yes, sir, correct. Sir.
I think some of you just woke up, you know. So tangent pi over 2 is equals to what? Tangent pi over 2? Tangent pi over 2.
0.027.
Are you sure? Please Check the calculator again. It's working.
It is 0.027.
Really?
Yes, sir, same.
Yes.
0.027.
0.027.
Yes, sir.
Tangent is sine pi over 2 divided by cosine pi over 2, right? So what is sine pi over 2? Sine pi over 2 is what?
Sine pi over 2 is 0. Huh?
Sine pi over 2 is 0.027, sir.
Same, sir.
Sine 90 degrees, I thought is 1, right? Isn't it? Maybe I pull up this table, the trig table, to show you.
It's 90 degrees, sir. Pi over 2. So sine 90 is 1.
Huh?
Yeah. So pi over 2 is 90 in degrees is 90 degrees. So sine 90 is equal to 1.
1, right? Then 1 over cosine pi over 2.
And cos
Cosine pi over 2. I'm going to come and beat you guys up. Luckily, you are far away from here.
0, sir.
0, so 1 over 0 is undefined, isn't it?
Yes, sir.
So 1 over 0 is
Yes, sir.
infinity, right? Then how can it
Yes,
be
sir.
0.027? So infinity. Zn, Z naught, ZL over plus J. Okay, so this part is infinity. Do you agree, guys? This part here that I'm circling right now is infinity, right? This is infinity, isn't it? Hello? Hello?
Yes, sir.
Yes, sir. Yes.
That part. So infinity times Z naught also is infinity, correct?
Yes, sir. Correct.
Yes.
So infinity Z naught plus J infinity right? Then how you do, because the way you do it is you divide through by the infinity, top and bottom. How to solve this? You divide through each term by the infinity. Or infinity, 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 Z naught infinity. What happened to this? Okay, sorry. I have to retain I forgot to retain this Z infinity Z naught here. I'm going to retain the Z naught over ZL. I mean, okay. Remember, Z naught ZL is still there. I'm going to keep them separately. The RF microwave class has become a mathematics class. So, okay, agree or disagree? Anybody? Algebraically is correct, you know. If you divide something by infinity, the numerator, you also must divide that. Okay. I'm using ZB for Z naught. Okay. ZB for Z naught. So I need to change all this to ZB. I'm changing all this to ZB. Because why Z naught is already taken here. Okay, let's, in this case, why don't I change this to, Z naught and then change this to ZG. For quarter wavelength, the input impedance Z naught squared divided by 2Z naught. So what do you want the input impedance to be? Okay, for maximum or disagree, because if we go back, sorry, we want Z in to be ZG. We want the name as the source impedance. Therefore, from here, Z in therefore from here, Z in is equal to Z naught squared over 2Z naught is equals to ZG. So solve for Z naught. So this is equals to Z naught over 2 is equal to ZG. Therefore, Z naught is equals to 2ZG. I say, hold on a second, please. I made a mistake here. Z yield is 2Z naught. So I'm going to change this to 2ZL. Okay, sorry, I have to redo this. Not quite redo. I have to relabel this again. Sorry about that. Okay, let's call this Z naught, and then let's call this a ZX or something, and then here to Z naught. So in this case, it's going to be ZX here. Just a small change in subscripts. Nothing to panic. So Zn is Zx squared over, okay. So that sounds, okay guys, the reason why I changed this, because we already have Z naught here at the output. We already have Z naught, the load as a function of Z naught, 2Z naught, and then we also have the source impedance Z naught. So I cannot call this Z naught also. I'm just calling this Zx. So that means the input impedance, the impedance looking into this is given by this formula. Okay, load impedance. This is load impedance. This is the Zx. Okay, this is a Z. Again, so there's one more thing that I need to change here. Is hold on here. I forgot to change this. Okay, this is also Zx. Okay, Zx is the impedance, the characteristics impedance of the cable. So the input impedance is the characteristics impedance of the cable multiplied by ZL multiplied by the whole thing here. The numerator is ZL plus J, ZX, tangent beta L, divided by ZX plus J, ZL plus tangent beta L. Okay, just a small change in the subscript. The most important thing to look is at quarter wavelength. Your equation reduces to at quarter wavelength. Quarter wavelength, Zn is this. This is Zn. This is the characteristics impedance squared divided by the load impedance. That's all I wanted to show. But I could have just written this, but then you'll be wondering where it came from. That's why I went through all these things. So now we know from this, using that formula Zn, we found Zn to be this value here. And next, we already know what our ZL is. ZL, the load impedance is given as 2Z naught. So I just plug it in. And then solve for. So what we want to solve here for? So we already got this. The next thing we want to do is we want to find out. So like for this is the circuit. This is a circuit. And this is the Zn. So what should be Zn for maximum power transfer? This is Z naught. So then I said for maximum power transfer, Z in, the impedance looking into the circuit maybe I redraw this here a little more carefully. So this is the ZG. Okay, now I'm so this is the cable here. This is Z in. So we already found out what is the Z in. Okay, again, there's another subscript that I forgot to change here. It's a ZX. See, remember, it's a CX here. So I have to keep it ZX. So in order to get for maximum power transfer, Z in must be equals to Z naught. Okay, Z in must be equals to the source impedance. Any question? Any question?